Solve. All right, so for example A, we have two logarithms on the left-hand side of the equation. That's actually a problem because we have this little rule over here which says that we can only solve log equations that have at most one log on each side of the equation. In other words, it's not going to be possible to solve that equation unless we can either condense those two logs into one, which is usually possible, or if we can evaluate one of the logs to remove it so it's not in the problem. So it turns out in this one we can actually evaluate that log of 9 base 3. This log of 9 base 3 is actually something we can do. The reason why I say this can be evaluated is because this logarithm asks the question, what power do you have to raise 3 to in order to get 9? Well, we can certainly answer that. The power we raise 3 to get 9 is the second power, right? So log 9 base 3 is just 2. So we can rewrite this as 3 times the log of x plus 2 base 3 minus 2 is equal to 1. And then from there, we're able to add 2 to both sides to isolate the log, right? Because when you have a log equation that only has one log in it, you want to isolate the log, right? Get it by itself on one side of the equation. So we add 2 to both sides, and we end up with 3 is equal to 3 times log of x plus 2 with a base of 3. So remember, when you have just one log left by itself in the equation, you want to isolate it, get it all by itself. We can certainly divide both sides by 3 here. So dividing here by 3 gets rid of that, and dividing 3 by 3, of course, gives you 1. So we end up with the equation log of x plus 2 base 3 is equal to 1. Now from here, to finish up, all we're going to do, once we have one logarithm on the left, a number on the right, we can then just switch to exponential form to finish the problem. Exponential form involves canceling out the log and then switching the positions here and here. Remember, the base always stays the same. So we're going to end up having 3 to the 1 power is equal to x plus 2, or in other words, 3 is equal to x plus 2. And then with that, we can simply subtract 2 from both sides. And we get that 1 is equal to x. So the answer for the equation is x is equal to 1. Now, we can check our answer by simply plugging that back into the original equation, which you should probably do. Let's just run that quickly to see what happens. We'd have 3 times the log of x plus 2. If x is 1, that's going to be 1 plus 2, or 3, right? And then that'll be minus the log of 9 base 3. And does that equal to 1? Well, whenever the two positions here and here match up, we can say that that log has a value of 1, right? Because we're asking the question, what power do I raise 3 to get 3? The answer, of course, is 1. So that means this is 1. So we have 3 times 1, or 3, minus, and remember this one was just 2, right? Because this just says, what power do you raise 3 to get 9? And the answer for that was just 2. So this is 2. So we have 3 times 1 minus 2, or 3 minus 2, and yes, indeed, that is 1. So the answer certainly works. All right, so let's take a look at example B then. You'll notice in example B, we have 2 logs on the left-hand side of the equation, but that violates this principle here that says we can only solve log equations that have at most one log on each side of the equation. There are 2 logs on this side of the equation. That's not acceptable. So we're going to have to rewrite them using log properties this time, because we can't evaluate these like we could in the last problem. We can't figure out, what log of x plus 2 is, for example, or log of x minus 3. That's not knowable because we don't know what x is, right? Before we had log of 9 base 3, that was something we could actually do, but we can't do these logs, so we can't evaluate them to get a single number out of them. So as a result, the only way to remove the extra log we have on the left-hand side is to rewrite the 2 logs as a single logarithm. This is actually possible here because they have the same base, which is very good. And then also we have a plus sign between them. Remember that the sum of logs can be expressed as the log of the product, right? So in other words, we're able to rewrite addition as multiplication if we want. So what we do to do that is we write a single log with the same base we had to start with, so log base 6, right? And then we take the product of the 2 things we were previously taking the log of. In this case, it'll be x plus 2 times x minus 3, and that'll be equal to 1. And then from there, once you have a single logarithm on one side and a number on the other, you can just write it in exponential form. That means drop the log and switch these 2 positions. So you end up with 6 to the 1 power is equal to x plus 2 times x minus 3. Now 6 to the 1, of course, you know is just 6. And as far as this other piece goes, we'll just have to FOIL and then solve the resulting quadratic. So x times x is going to give you x squared, and x times negative 3 is negative 3x, and then positive 2x, and then lastly negative 6. So from here, we'll bring the 6 to the other side to set the equation equal to 0, and we'll combine like terms, right? So I'm going to subtract 6 here, subtract 6 here, and then I'm going to combine like terms. So we'll end up with 0 on the left-hand side. We'll have x squared. If I do minus 3x and a positive 2x, I get a negative x, and then of course I have minus 12 when I do minus 6 plus minus 6. Then from here, I can factor and try to solve. So it'll be x and x. And then I need factors of 12 that subtract to give me negative 1. I think 4 and 3 are 1 away from one another, so I'm going to use 4 and 3. And I want it to be negative, so I'm going to put a minus here and a plus here, right? And then from there, that's equal to 0. So I have my factoring accomplished, and then I'll have x minus 4 is equal to 0, and then x plus 3 is equal to 0. And lastly, then we can see that the answer is going to be either that x is equal to 4 or that x is equal to negative 3. Now, it turns out that we often end up having solutions that don't work in the process of solving log equations. So we need to check our answers. The reason why we need to check them is because we know that in the domain of a log function, we're not able to put in any number that is not positive, right? So we can't put 0 into the log, and we cannot put negative numbers into the log. So what would happen if I plug negative 3 into this statement here? Well, it'd be log of negative 3 plus negative 3, which is negative 6. And log of negative 6 is not defined. So we're actually going to have to cross out this answer and say that won't work. 4 will work, however. You can put 4 in there. You'd get log of 4 plus 2 in the first statement, which would be, of course, just log of 6, base 6, which is 1 actually. And if you plugged 4 into the other one, you'd get log of 4 minus 3, which would then give you 1, and log of 1 is always 0, and so the answer would check out. So it turns out that x equals 4 is okay. So that's our only answer. X is equal to 4. All right, so let's take a look at example C. You'll notice that we have just one log on each side of the equation, which according to this rule then means the equation should be solvable. However, I don't know how I'm going to handle this situation, right? I can't just drop the logs because I have this 1 in the way, right? If there was no 1, if it was just log of 3x plus 9 is equal to log of x minus 4, I would be able to just drop the logs because they have the same base. Remember, if the base is not written, it's assumed to be 10, so it's the common log. If there wasn't the 1 there, I could just drop the logs. So you'd basically be taking the log of both sides of the equation. So, of course, the only way that the two sides would be equal to one another is if what you were taking the logs of were equal to one another. So we'd be able to do that if there wasn't this annoying 1 in the way, but the 1 is in the way. So we're actually going to have to move the logs together on the left-hand side of the equation. So we're actually going to have to say minus log of x minus 4 to both sides of the equation. Now, this sort of then brings us to a situation where we end up having two logs on one side of the equation, which we know we can't have, right? So that will remind you that then you have to rewrite this so it's a single log, which is okay. They have the same base. This time there's a difference between the logs. Remember that the difference of two logs can be expressed as the log of the quotient, or in other words, you're going to rewrite that log just once. So just write log base 10 here, and then divide the two things you were taking the log of before. So it'll be 3x plus 9 divided by x minus 4. And that should be equal to 1. Now, once you have it written so there's a single log on the left and just a number on the right, you can switch to exponential form. Don't forget there's an unwritten base here of 10 for the common log. So we'll drop the log and switch these two positions, right? Keeping 10 as the base, this time the base of the exponent. It'll be 10 to the 1 power is equal to 3x plus 9 over x minus 4. Now that's the same as saying 3x plus 9 over x minus 4 is equal to 10, right? So let's solve that equation. So we can, for example, cross multiply. I can multiply x minus 4 times 10, right? So we end up having 3x plus 9 is equal to 10 times x minus 4. And that, of course, will be then 3x plus 9 is equal to 10x minus 40. Then it's a normal linear equation, so add 40 to both sides and subtract 3x from both sides. This is going to get the x's alone on one side and the numbers alone on the other. So the x's cancel out. We end up with 49 here is equal to, the 40s cancel out on the right, and 10x minus 3x is 7x. And of course, you divide both sides by 7 to finish. And you end up with the idea that 7 is equal to x, because 49 divided by 7 is equal to 7. All right, you should always check your answer in the original equation to make sure that it works. So let's go back here. So here's our check for the problem. In our original equation, we had log of 3x plus 9. That will be now 3 times 7 plus 9 is equal to 1 plus log of x minus 4. That will now be 7 minus 4. All right, so this will become log of 21 plus 9, which is 30, is equal to 1 plus the log of 7 minus 4, which of course is 3. Then from here, if we subtract the logs from both sides, right? Then we end up with log of 30 minus log of 3 is equal to 1. Now remember, a difference can be expressed as a quotient, so it ends up being log of 30 over 3, which is the same as log of 10. And that's base 10, so yes, it's true that log 10 base 10 is equal to 1, because we know whenever the base and the thing you're taking the log of match up, the answer is just 1. So this checks, and we can say that then 7 is equal to our answer for C.